I'm getting ahead, so, but you've defined speak h-nil, and you've defined speak int, and you've defined speak tail, I think was the third.
I called it non-int, yeah.
Non-int, right. So all you have to do is be able to speak the head of the thing and speak the tail of the thing, and you can do everything.
Yes.
Except that the non-int, we might want to also be able to start with a double. If you have a double as your first, as your head.
Yes.
And then whatever the tail is. So you might define a speak double and a speak not double. How do you have everything except int and double?
I think I'll describe one part of this technique in a second. I want to emphasize the way that you've mentioned that. So the question was that the way it currently works is it's sensitive to int and not int, but it also could be sensitive to int and double and everything else, right? And so like, how do you maybe expand the specification to cover more cases? And what you would do is you would just define speak int, speak double, and speak everything else.
Everything else.
Yeah.
Okay.
And we'll show you how to make that, or I'll show you how to make that more clear in literally like 2 more slides. So,
Thanks.
Cool, thank you. So let's get back to where we were. So before I get into that, I want to say this. This is kind of the standard interface, and a lot of shapeless functions will look like this. Because if you look at shapeless, it doesn't make you use all these traits and everything, obviously. It actually is using them all behind the scenes, but you'll see actual like value level functions. So if you look at this, speak, def, speak here, it's a function that works on any input hlist and gives you the output out hlist in exactly the style that we've been describing. It does the speak functionality. It just requires, sorry about the 3 there, it just requires that you define that there's an available speak instance for that input type, right? So this is just the final thing. It's just like a surface syntax that makes it a little bit nicer. If I want to just call speak on an hlist like I did when I first introduced speak, then I just ask for an implicit version of the trait that gives me the functionality, and then I just call that trait. So this is just purely to demystify the fact that you will see a lot of functions that don't look like traits.
Are you saying trait instead of type class?
I am saying trait instead of type class. I'll just say type class if anyone has any issue with that. Awesome. Yes?
And it sounded really important.
Oh.
Please review what you guys just said. That's briefly.
I asked him, did he say trait instead of type class?
And you said it's an equivalent.
I would consider this to be a way of using traits that's all inside of the type class pattern. I'm saying trait because that's what I write, and I didn't want to introduce type class unnecessarily, but if everyone's comfortable with me using type class, all of these traits are of the type class style. So type class is a reasonable way to say it. Right. So the overlap thing that I've talked about several times, let me just drive it home. Speak int and speak non-int overlap. I could choose, if I have an int on the head of the list, I could choose either one. One of them does the right thing, the other one does the wrong thing. So I shouldn't choose the wrong one. To do that, this is a common trick you'll see in a lot of different type class libraries, and you'll see it in Shapeless. You do this low priority implicits thing. It's the last little tricky piece of implicit resolution technology I need to use. The way it works is that if you are resolving implicits in an object, like the companion object, like we're doing, and you have an inheritance tree on that object, it will try to use the direct ones before it will do the ones in the inheritance tree. So if I want to make some implicits less likely to be used, or to be used later in the search process, I need to put them into the superclass of the companion object. So the convention is you just make a trait with the same name as the companion object, underscore low priority, and then have it inherit from that. And so you can see the speak nil and the speak int instances are defined in the object directly, and the speak non-int is defined in the low priority implicit that it inherits from. And that just makes the type class or the implicit resolution machinery do the thing you want it to do. And it's a really good example also with as you're extending this function, because all of these kind of fallback things are everything else cases, you stick them in a low priority object. Again, in this case, it's not even necessary, but it's good for reading. Makes it a lot more obvious that that's a fallback case. So that's one way to improve it. And then we're going to run into this issue. So before I get into the next issue, is that all making sense so far? Are there any other questions about speak? Hopefully this machinery. It's actually all of the machinery. I'm just kind of going to refine it and polish it from here. But if it's sort of making sense at this point, then I think we're well on our way to being competent, wonderful type-level programmers. Awesome. Feel free to ask more questions later, too. So here's a big issue. I just said everything that we did was pretty much everything we need to do. That's kind of true. It also isn't true in the sense of it totally doesn't work. You can stick hlists into it. Scala will happily compile. It will happily run. It will even happily give you the right answer. It's just the output type of the answer that gives you is something subtly different from what you want. And if you look at that, it even kind of looks like the thing we want. Oh, if I call speak on hnil, it gives me speak.speakhnil.out, which is hnil. Right, that's the right type. So here's the issue. Or maybe I'll double down and say the other one too. If it's a 3 hcons hnil, the output type of that is speak of int hcons hnil, its projected out type, whatever that is, which is string and hnil, right? And that's the issue. We know it's that. We know exactly what that functionality is. We can read that, and the first time I did this, I think I was confused for hours because I was like, it's working. It's doing exactly what I want. And then I can never use it again because the big secret is, let me see if I wrote it. Yeah, we're not retaining the type information. As soon as we call speak on it, it's throwing all the type information again. If we work so hard to not have it do that, it just threw it all away. The reason is that type members are by default opaque, which is to say Scala will believe that if you give me an object and you ask for its type member, that type member is a type. If it's got a type bound on it, it will believe that it has that type bound. But it won't believe anything about what that type is. We know that the output type on that second example is string hcons hnil. And Scala technically has all the information to infer that. But until you beat it over the head and say, retain that information, it's happily just going to forget it and tell you, oh, it's out, whatever out is. And that's a reasonable thing to do, too, because if someone made a pathological speak instance, it could still have that type, and we don't actually know that it has the right type. We just know because we know what the functionality ought to be. So we need to tell Scala, actually retain all that type information, keep it around, smash it together, use it on the outputs, and let us follow through and be able to compose multiple type-level functions together and have them all work. I will say, also, as we're about to dig into this functionality, this technique, this is probably the thing that will burn you when you go off later and try and write one of these things. You'll forget about this, or you won't do it quite right, and you'll get these opaque types, and everything, it will just seem like everything's broken. You're super close to the answer, and you just should do this one thing, this is the way I suggest you do it, and then it will make it work. It's just fragile, and I'm sorry about that. So we're going to use refinement types for this, which to certain mentalities should set off warning bells because refinement types are kind of an advanced Scala language technique, and it doesn't work in Scala.js, and it uses runtime reflection and all these kinds of things. We're not going to use any of that. We're going to actually use one little piece of refinement types that only actually behaves totally nicely and doesn't do anything weird and doesn't require reflection. So still no reflection. Tiny little bit of refinement type. I'm going to change that top line to the second line. Now, in case I wasn't familiar with refinement types before I ran into this, so I'm going to go through this kind of in detail. Everything on the second line after speak is a type. It kind of looks like I'm making an object definition there, but I'm not. It's a type. Scala supports, after any object type, opening up a brace and then adding more information into it. And that's what refinement is. You're refining the base type with some extra information. And that's exactly what we want. We have a speak that we know takes an input of int and hnil, and we need to refine that to also write in what the output type ought to be. This is exactly what we did here. We refined the speak to also carry around the output information. And the trick is we need to use those everywhere that we have that information, and then Scala will have it available and will chain it along for us. We didn't do that earlier because it seems completely non-obvious to do that, because it is, but that's what we need to do to make Scala behave properly.
If you would write both of these definitions in one program, would it mean that there's two different unrelated types, or it's not compiles, or? Yeah,
they are different types. They're not unrelated in that I don't use these a whole lot except for this purpose, but I'm going to guess that they have a supertype-subtype relationship. Scala will be happy to forget about refinements if it needs to. But they are literally just different types. One of them contains some more information. It's another rich type, but just harder to use.
Does the speak
Shh. Yes, it's the aux pattern, exactly. I'm not even going to get very far. We change h-nil to the refinement type. It has the output type now defined. So when we define that rule, this is the thing I was saying earlier, we can now read the output of this val. The type is actually giving us all the information we need. The input is h-nil, the output is h-nil. It's all right there. You can read it all at once. Scala can read it all at once. We could just do that. That works. If we just applied that to all of our implicit definitions, it would be totally happy. I'm not happy with it, though, because that's like, I don't know, 12 characters, and I'd prefer it to be more like 7. Also, you'll just see this thing a lot, the aux pattern, as, sorry, what's your name? Ari. As Ari pointed out, the aux pattern is it's just the name that people have chosen to use to describe this pattern, and you'll see it a lot. So here's what the aux pattern looks like. I'm just going to, in the companion object of speak, define this type alias called aux. It takes in all of the same type members as speak, which in this case is just in, and it takes in also arguments for all of the, sorry, I said type members. It takes in type arguments for all the type parameters and all the type members. You have to append 0 or whatever to all the type members here, because otherwise you'll say type out equals out, and Scala will imply that you meant a loop, which is not right. So essentially I just gave a type alias for that refinement type. That's all. If I say speak, sorry about the 4, I'll just explain that. I call it speak 4 because if you look in that repo, there's speak 1, 2, 3, 4, which is each one of these refinements that I'm adding on to it. So this is the working version, 4, the last one. Speak.aux, h-nil means here's a speak instance that takes in h-nil and returns h-nil. It's just that refinement type again. Speak int here now takes an aux type as well. Speak 4.aux int hcon's tail returns string hcon's tail out, which just means that we're also going to manipulate the tail piece of it using that implicit tail argument, right? So hopefully this cleans up the kind of concern that you were talking about earlier, where we didn't have the information about the output type. It was in there, it was being defined on the traits, but it was all opaque and hidden. We've elevated it up so that it's available for reading and also for Scala. When it starts to pull these instances together to build your implicit, it will have all the output information it needs, and it will glue it together properly. 3 stars. Any questions about the aux pattern, hopefully? Yes.
So, in the previous one, if I remember right, it was outputting an in and h-nil. Way back when I asked the question. But here, why is there a string : tail out? I'm missing something very fundamental.
I think earlier, so the question was, earlier it looked like it was outputting int : tail. But now it looks more clearly like it's outputting string : tail.out, right? And like, why is it suddenly giving us this extra information? And what was going on before when it looked like the output was int : tail? And again, that's kind of the big sneaky bit of all of this, is you have to keep track of your inputs and your outputs kind of carefully until you get used to the pattern. Until you have the aux pattern, or until you're using refinement types, there's no way to talk about the output types of anything you've written. They're all buried inside of the objects as opaque things. So all of the types that you see, they're always actually input types until you start using the aux pattern, until you start using the refinement type. So when you were looking at it before and you saw the int : tail bit, it looked like an output type because it's just really easy to read it that way, but it actually was defining the input of the speak function that was going to return some unknown output that we only just now have the technology to talk about.
Okay, I think I understand now. The type aux, square bracket in out, that's the signature that is redundant, because you're calling speak 4.aux, and that's the signature of aux.
Yes, yes.
Because the first one is the input, and the second one is the output.
Yes.
And for us, the first is the int type, and the output is the string type.
Exactly.
Okay, awesome.
Cool. Thanks. Oh, I think he was first, but then
How does the aux pattern work with the low priority trait? Would type aux have to be defined in the low priority trait instead?
No, there's nothing special about the aux type. It's just a type alias for the refinement type.
Right, but can you use it? So we have speak non-int in the low priority trait.
Yeah.
but you want to return a speak.aux in there.
Oh, I think that just works because it resolves it recursively. Yeah.
Is aux the first actual shapeless thing we're using now? Because it seems like everything we've done doesn't require shapeless.
Everything we've done so far, H-list is the first shapeless thing. That's actually defined in shapeless.
Right, okay.
Aux is actually not defined anywhere. Like no one makes even like a trait of things that extend and define aux. Like it's just a heuristic, a pattern. You'll see it places. You could call it anything you want.
Cool. Okay.
Yes, that's a great point. Aux is not special. It's just a name that people chose. I don't even know why. I don't even like it very much. But it is the one, and you'll see it places, so you should get familiar with it. Many things in shapeless will define on their companion objects an aux type. And that's kind of when you know you're playing in type level land, is because everyone starts defining aux types, and you're like, oh, okay. That's where we're at now. Cool. So this is basically the end of me explaining type level programming. So like, I feel like if there are any other questions, we can talk about that. It's 2:13 now. That means we've been asking a lot of great questions. I wanted to maybe spend a little bit of time doing exercises here, but I also want to get through generics. So I'm going to talk through some exercises and honestly kind of offer myself as much as anything else, or you guys should maybe find partners who also went to this class to go through the exercises in time you have later. And I'll try and kind of push through and see if we have time at the end. I would like to get through stuff and then have spare time at the end to work on exercises together as well. So I guess my point is I want to kind of push through here if everyone feels comfortable with that. Cool. And again, I really appreciate the questions because I think like that dialogue is important because they're things that's hard for me to talk about until someone asks the question. Speaking of.
One thing here, the types that you're having to put in front of the definitions of these functions seem to be larger than the boilerplate you're getting rid of.
Yes. This is a question of when should you use shapeless, kind of. If we're going to write all of this to just give point2D an automatic ordering method, then that's terrible. You only do this in a library setting when you're going to pay a lot out in your users saving boilerplate. Like speak is a terrible example because nobody writes speak, but we'll do ordering in a second, and we'll essentially be able to write ordering.derive and have it just derive the ordering for point2D or for I have a recursive binary tree because recursive types are fun. And if somebody is defining a bunch of these things and they want free ordering on everything, then it's worth maybe doing this work to do that. Ordering, again, might not be even the greatest example, but a lot of these type classes, type class pattern often has a lot of these like, I just want the obvious implementation. I don't want to think about it too much. If you guys are familiar with Haskell, it has a lot of this built into it. It's lovely. You define a type and you're like, give me show, eq, ord, typeable, give me a hash on it. Like you start naming things you want and Haskell's like, cool, got your back. Scala only does that for equality on case classes and pattern matching and things like this. So it's a good way of extending that kind of, that's kind of where I think the sweet spot of usability is like if you just want to define a bunch of types and have some functionality appear on all of those types, then you pay this madness one time and then somebody pays out a lot later. Yeah, great question. Cool. So, ta-da, this works. And for fun, for people that, this is worth saying, IntelliJ is not really great at type level programming. You should often double check with Scala C because IntelliJ will be like, that makes no sense at all. And then Scala's like, actually, I'm totally fine with that. In this case, though, at this level, doing it this much, like a simple kind of example like this with all of the bells and whistles, but you're not combining too much stuff, IntelliJ is totally fine in inferring that type even. So if you do it, you get it in this weird, terrible, not infix syntax thing, which is hard to read, but it will infer the type and it will be right. All right, so what makes a proper type level program? Just the things that we described here. Define a trait, use implicit vals to define the base cases of the traits, DSL for creation, use implicit defs to define the recursive cases, use inheritance to deprioritize certain cases if you don't want them to be the dominating ones, and use the aux pattern to expose the type member information, otherwise you will not get any output types that you want. That's the highlights. Some exercises, again, I'm going to skip over these for now, we'll try and do them later perhaps, but these are simple things you can do. They're in the slides, they're in the book, and I haven't actually put any answer code anywhere, but maybe I'll do that after this thing. You can write a type level function that takes the head of an age list. Seems kind of simple. It actually is a type level function. It should be sensitive to whatever the head is, but it doesn't require a lot of the pieces that we just described. It's a very simple one. A little bit harder is you can do one that doubles all the elements. So it turns 3 H nil into 3 H nil, true 3 H nil into true 3 H nil. And that requires creating an output type, so you have to use the aux thing. It requires thinking a little bit about how the recursive cases work. They're all fairly simple from the level of the recursion on the values is really obvious, but getting a practice of how to make the type machinery work is, these are probably some good examples to try that out. With all that, let's get into generic programming. Any last questions before you get out of this? Generic programming, we're going to do more type level programming. We're going to see these in further examples, so it's not going away, but like, yeah.
Yeah, so you mentioned search like a while ago.
Yes.
I don't know, are you going to like return to it and tell us like what's a good alternative?
Good alternative to Cersei? Or?
Yeah.
I'm not going to speak about Cersei.
Okay.
I will show us how to do Cersei's semi-auto deriving in a couple, that's the next section. And toward the end, I'll talk a little bit about, like, kind of to your question, when is this even worth it? But yeah, this next section will be more like Cersei. So here's the example. Hey, we saw this one already, point 2D. I want to put ordering on it, and I want to do it like that. I just want to say, give me an implicit ordering for point 2Ds, define it in the companion object, and how do I define that ordering? I just say generic ordering.derive, just like Cersei semi-auto, if people are familiar with that. And that works. By the end of this next section, we'll do that for point 2D. Binary trees. They're binary trees. It's a recursive type. The reason I'm doing this is because recursive types are more complicated than non-recursive types. Are they more complicated to derive? Yes, but only because it also has a type parameter. So for derivation of a type parameter, you have to have in place that the A inside of the tree is also orderable, right? And then we just use generic ordering.derive. So generic ordering.derive, that thing's where the power pays off for all this madness. If I want to just derive ordering for anything, I just drop one line in there and make the implicit available. Or I could even pass in generic ordering.derive directly as an argument to something that needs an ordering. Like, you don't need to define the implicit here, it's just convenient, right? So this is generic programming. This is the whole payoff. I did all the stuff we've talked about so far is to get to this point. And it's going to be kind of remarkably simple because we're all expert type level programmers now, and this is just a fairly simple type level program on top of the one last thing that Shapeless really provides. And so you were asking, what does Shapeless provide? H-lists, and then this. And this is generic. I'm going to dig into what generic means, and I'm just going to say it right now. Shapeless is going to automatically provide you generic instances for every case class. That's the really cool thing Shapeless does. It uses macros. Nobody likes macros, or maybe people like macros. Everybody likes to hate on macros, including me. And it uses macros, but the kind of thing is it's going to use some macros for you to produce a simpler way, a simpler representation of types, this generic representation of types, which is easier to work with. And then you can forget the macros ever exist. And Miles Sabin and all the people working on Shapeless will test the crap out of those and make sure that they always work. But as far as we're concerned, it just magically provides generic instances for every case class. So what is generic? It's a trait, it's a type class, and it has three things in it. One, a type member called repr, which is representation. This is the whole thing of generic programming. We have some type, like point 2D. And we happen to kind of, I don't even know what to call this relationship yet, but we happen to know that that thing's pretty heavily related to this guy. And generic helps us to represent that relationship. Generic says, well, if the generic of point 2D is going to have a repr that's similar to the structural type for it. In particular, it's going to be an H-list. So repr is whatever that H-list type is that represents the T that your generic instance is for. I'll note that it isn't actually bound. There's not a type bound here saying that it must be an H-list. This is, again, to handle that coproduct thing that I'm not talking about. But for purposes of today, they're always H-lists. Generic also provides two members, to and from, which are the value level mappings from the representation and the root type back and forth. So the law of generic is that if I have an instance of generic for some type T, I can hit that type or values of that type with to take them to the representation, and then I can hit the representation with from to go back to that type. And so the whole trick of generic programming is we're going to ask for generic instances. We're going to to all of the inputs into the generic representation, do all of our work on the generic representation, and then from all of the outputs of that work back into the type. And then you're done. That's generic programming in the shapeless way. And we actually kind of have all of the tools we need to do everything that I just described there. As soon as you have generic instances for all of your case classes, this just becomes a type level programming exercise. So we should be able to do it given the stuff that we explored earlier today. Let's dig in. First, to make a program work generically over all case classes, like I just said, but just to lay it out there, you write a type level program that works over H lists of whatever the constraints that you need. It's like for ordering, we're going to make a function that works over all H lists that consist of element types that are also orderable. They have ordering instances. So we write the generic program for all H lists. We transfer that functionality to case classes using generic. And I thought I had a longer list, but that's actually it. That's all we do. Yes?
Maybe you'll cover this, but like, what about sometimes? So if my trade has, multiple case classes, like...
Some types like that, SUM, yeah.
Yes. So you just literally do this multiple times? I guess what I'm really asking is, how does Shapeless know which type an HList will map to, or do you have to tell it? You got to tell it, right? So I'm going to do the thing I said I wouldn't do and talk very briefly about coproduct.
Okay. I am living in a world right now where some types do not exist for purposes of exemplifying this, but because you asked the question, because it's a great question. This also works. Shapeless provides generic instances for all case classes and all sealed traits containing case classes, which for people who are familiar with algebraic data types are sums and products of types. It provides all of them, and all recursive. They can also recurse, but that doesn't really matter because you'll have to call to a bunch of times to recurse them. Anyway, to represent product types, we use HList because HList is kind of a generic product. To represent some types, you use coproduct, which is almost this exact same technology, except instead of having a double and a double, you have a double or a double, right? Some types. So coproduct does all the same stuff, again, allowing you to have this ORs. And then when you ask for a generic thing, I said the generic representation is not always an HList, because sometimes it's a coproduct of HLists. And then you just work on that generic representation. This is the sum of products representation, which is one way of doing generic programming. But that, great question. I was trying to avoid it, but it's a great question, so thank you. All right, so where are we here? Oh. So we're just going to do those two things. To implement this thing, we're going to write compare HLists, a lexicographic ordering type level function that works on all HLists as long as all of the elements of the HList are themselves also orderable. Otherwise, it would make no sense. And then we'll define a thing called generic ordering, which is a trait that just translates compare HLists to all case classes. So let's dig in. This looks a lot like we just did a second ago with speak, except there's no output function, or there's no output type, because the output is just a constant int. You don't need to use the output type member if you don't have a complicated, rich output type. So we don't. Apply takes in one element of HListL and another element of HListL and gives you an int using the normal comparison int trick that Scala does. We can define it for HLists. HLists are equal to one another, so it always returns 0. HNil, thank you. You can do it for HNil. HNil is equal to HNil, so the comparison is 0. And then we can do it for HCons, which says if we want to do something for an HList that has head type H, HCons tail type T, then we need to have an implicit ordering for the type H, right? Because otherwise the elements of our H list are not orderable and we're in trouble. And we need to know how to order lexicographically the tail of the list in case we need to fall back on the tail, right? So we require those two things implicitly. And then we build the compare H list object, which just takes a look at the head, uses that implicit ordering we pulled down to compare the heads. If they're equal, then it defers to the tail, and if not, then it returns. That's a bug. I fixed that. I fixed that in the code that has test. I'm so sorry. I should have copied and pasted again. It returns else. It's if compare head equals 0, then we recur, else return compare head, not 0. Otherwise, that's a bug, obviously. Sorry. So I'm being really flippant about this because it's simpler than the stuff we were doing before. Hopefully me going through this quickly is still kind of familiar. It's another instance of type level programming. Does anyone have any questions about compare H-lists? Everyone's looking really intently at the slide, so I'm going to give everyone a second. Yes?
So if I have to do this for a generic type, and by generic I don't mean just generic, but like let's say a list of a variety of things, or wants to do it for a map, let's say, compare the keys of a map, then how are they going to employ it? Like, they are not going to write a map class that extends from H-list or H-map. Like, how does it sort of translate to other data types and stuff?
We're going to use generic to translate this to case classes, and it's only going to work on case classes. It'll work on any case class. Like, you define a new case class, and it automatically works for that case class, as long as all of the types inside your case class are themselves orderable. Otherwise, it wouldn't make any sense, right? But to start applying it to other kinds of data structures, like maps or something like that, is not really the place where this is going to work. You're going to need to use maps. If you're working with maps, you'll need to use the map functionality normally. This is mostly just about working generically over case classes, or as he pointed out over there, sealed traits or sealed hierarchies of case classes. Yeah. You could do type level programming to make the kind of stuff you're talking about work. It's just Shapeless doesn't really do it, and I'm not going to talk about it. But the doors are open here to doing really crazy stuff, if you want to go that way.
And the reason why it works for serialization and deserialization is because most of the objects that we want to serialize are case classes.
Yes.
So we are able to convert them back and forth between the object and the case class.
There's a really, that's true. It's mostly working on serialization and deserialization because the primary lift of making serialization and deserialization work are things like case classes. Cersei also defines how to serialize a map and a list and other things as just other implicits that it searches for. But the lift is interesting because the challenge of making a serialization library is that you want your users to have it work over all of their types. And they're going to just keep creating new types. And when users create types, they're probably going to create things like case classes. If they don't, then they have to do some more work, but they often, in Scala, will create a lot of case classes, right? So if you can make extending your serialization library over user-defined case classes easy, then you've reduced the work a whole lot. But then you have to do some other things to make sure that lists work and maps work. I'm not really going to explain how all of Cersei works, just this one piece. Cool. Yes?
So, let me recap. So, I think what I heard you say is that you can convert between any case class and an H-list. With a to and the from, you can go both directions.
Yes.
Only case classes or tuples that can be turned into a case class, or case classes can be turned into tuples. So you can actually use tuples, right? I can have an int, comma, string tuple, and that can get converted to an H-list.
Yes.
I can put almost anything I want inside a case class, so I can put an H-list inside a case class, or a map inside a case class. So I can actually use Shapeless with maps and anything that I can put inside a case class.
Yes. You'll use it with maps in that the types, the component types of your H-list, Shapeless doesn't care about them. It's just going to shuffle them over into the H-list, right? So the fact that one of them happens to be a map, Shapeless just doesn't care. The interesting thing is, I should bring up one thing you brought up that you maybe just guessed at, and I didn't say it explicitly. Tuples are also given generic instances, I believe. I don't really use that very frequently, but generic instances are defined for things that it's reasonable to define generic instances for, which is mostly case classes and tuples. But then, when you have like a map inside of it or something like that, like I guess I already said it, it's opaque. Shapeless isn't going to care about it. If you want to have a case class that has a component case class and you want to generic both of them, then you'll have to have both generics. You have to walk into the first one, walk down the H-list, find that other one, generic it, dig in more, and so you have to kind of recurse down the case class or down the H-list and like in another direction as you keep generically unbinding things. That's really complicated, but you can totally do it. All of that stuff's available. This just gives you kind of the basis tools that you would use for this stuff. Cool. All right, let's dig into this. Extending compare H lists to work on all case classes. The whole point of all of this. Here's the magic function that we want to write, derive, right? Derive of some type T. What do you need? Well, you need a generic instance for that type T. That's going to constrain it to be a case class, basically. Or again, a sealed hierarchy of case classes, but a case class. Otherwise, we wouldn't have a generic type. Or a tuple. Anything that has a generic type. Tuples, case classes. We need a compare. And that compare needs to be the appropriate compare for whatever the representation of that type is. So we do compare HList of g.repr, and then you'll be able to generate an ordering from that. Except I already gave away the ghost with my comment there that that doesn't work. That's really what we want, and if we could write that, and as far as I can tell, there's no reason we can't write that, except Scala just didn't put it in the way that implicit argument lists work. I think there's even a SIP out there to make it work. That is really what we'd want to write, in which case it'd be very easy to use it, because you just use the generic to map the thing into its representation, compare the representations to get the ordering, return the ordering. Ta-da. But we actually have to do a couple tricks to get around the fact that this is not legal to write. And the standard trick for type level programming is make a new trait, right? So we'll make a trait. Call it generic ordering. This is the same kind of type level program we've been writing. For any type T, we can pass in two elements of that type T, x and y, and we'll get out an integer. That's what we want generic ordering to do, right? And then we'll have implicit, sorry, this should be implicit def, no, it could be, if you make it implicit, then you'll get different functionality. We're not going to use that right now. We def the derive by just saying, in order to derive an ordering for a type T, we have to have an implicit value of this trait that we just defined, this type class we just defined, right? So that's the indirection that you need in order to make this thing work. So the last thing we need to do is define the implicit cases, which give the functionality to our trait, the type level functionality to our trait. So let's think about what we need for that. The implicit case needs to ensure that T has a generic instance, right? So it's going to look for an implicit generic, call it G. It needs to ensure that g.repr is an H-list. And we need to make sure that we have an implicit instance of compare H-list for that g.repr. That's the thing that we just wrote in that function definition over there that doesn't work. Just said it again, because repetition. We just need those three things to live. And so there's one last trick. I guess I call it two tricks, but one last trick to making this work. And that is when you're writing implicit cases, you can introduce type variables, like this repr type that I have, and use that to satisfy constraints that you need. So you notice that nowhere in this definition do I use g.repr. That's a totally valid thing to use in some places, but it's hard to do it in a case definition like this or a def like this. Instead of using g.repr, I introduce an unknown repr type. I don't know anything about it as of that first line. As of the third line, I know that whatever generic instance I find, the output, because we're using the aux type, right? The output type, the representation type of that generic is the same as repr. So now we've constrained that new repr variable I introduced to only work for some generic instance that you can find that also hits T. So asking for that implicit generic is going to relate T and repr together in the way that they must be represented, or they must be related by generic, right? I'm saying this over and over again because it's kind of weird. It hopefully kind of makes sense, and it might be kind of thing that when you do this, you'll have to struggle to remember or figure out how to wire it all together, but it should make sense. Then, now that this repr type is a stand-in for g.repr, we can ask for a compare H-lists that applies to that repr, and then we just do the thing that we said. We just order the representations that we get by calling g.to on x and y. The functionality is very simple. So, I've been saying a lot of words about this slide. I literally had 3 slides leading up to it because this introduction of a type variable thing is a weird trick. If anyone has any questions about that, please ask. This is like a prologue trick. It's basically the only real prologue trick you need, but it does show up. Yes?
Can you go back to the slide where you said it was illegal to, yeah. Couldn't you take the repr type parameter here as well, and instead of taking a generic, take a generic.aux?
Great question. You could. The reason, fantastic question actually. There's a very subtle reason why I wouldn't do that. And that is because then when somebody uses the derive function, they're going to need to pass in t and its representation, which means they need to do all the work. This will, the way the inference is going to work is it's going to say, okay, you gave me t, and now I'm going to go look for implicitly some generic, not this, in this definition, I'm going to go look for some generic ordering that works for t, and then when it actually tries to resolve implicit instances of generic ordering, it has all of the Prolog engine to start introducing new type variables to constrain and to work over to find the right instances of it. So it will do all the inference for you. Great question, though. That was a really good catch. Yes?
Can you take a look again at the implementation of generic aux?
I actually didn't even define that, but I can just give it to you. This is kind of what I was saying. Aux is just a common name. There's nothing special about it, but it just, if you read an aux, you should always be able to read it as. Good. I'll go ahead and write it anyway because it's a great question.
You use the generics method.
This is the companion object of generic. There's a type alias called aux. It has t and repr 0, and it equals, generic of t, structural type repr equals repr 0. And that's just defined in shapeless for you. And again, we could not use the type alias if we wanted to just write this structural type. Again, it's saving a couple keystrokes, and frankly, I find structural types really ugly. I guess people generically do because they use aux all over the place. There are other reasons. This is such a flexible syntax that it's easy to write a bug here. Like, oops, now that will still compile, it just won't work. Yeah, so aux is a useful pattern, but you'll just see it. People just use it, and they anticipate that the way you'll read it is the first couple arguments, like aux of t1, t2, t3, t4, t5. You see one of those, the way you read it is you say, the first however many types, those are the type parameters just being used again. The last however many types are the type members just being used again. Let me go look at the definition of whatever this aux type is in the companion object of and figure out what the parameters and the members are, and then I'll know what all those maps are. Like that's, almost always what the aux pattern will end up being. But yeah, great question. Yes?
Just real quick, in this implicit def line, the T is the type of the case class, and the repr is the type of the H list that corresponds to that case class?
Correct, yes. Yes?
Answered part of my question, but it's related. I think I've lost, or I didn't follow why we have repr in the first place. Like, why is it more desirable for us to work and manipulate that than the original key?
Yeah, this kind of links back to the thing I was talking about at the beginning of if we have point 2D, we have point 2D, we have double, toil and trouble. These two, they probably shouldn't be subtyping one another. Like, that doesn't really make any semantic sense. But you also can't look at those two, especially knowing that the representation of this behind the scenes is a double-double. You can't look at the two and say those are unrelated. So I want to build some way to build that kind of relationship in there, because this thing is easier to work with. As long as I don't care about the semantic meaning of point 2D, this is a much easier representation to work with.
Why? Is it because the repr is always an H-list representation, and it's got to define the person structure?
Yes, that is a big piece of it. Yeah, it's basically that. The repr is not some arbitrary type. It's always going to be an H-list or coproduct. Again, I'm not talking about those, but it's going to be some rich type that's easy to manipulate.
Okay.
That's a great question. I didn't say that explicitly. That's exactly right, though.
Probably did, and it just got lost in the whole thing. Thank you.
No, yeah, exactly right. It'll always be something rich. It's not even a tuple, actually. It's going to be the H-list type. Yeah, and then we just call that generic is the relationship. All right. So again, with something that should be relatively simple in that it implies only one new kind of trick over the type low programming we were doing before, this is enough to define generic ordering for any case class. Given that definition we had before, again, I'll go back to it. When I wrote point2d all the way back here, I just wrote one line saying, let me have a derived ordering and derive it with this one line, this generic ordering thing we just defined a second ago. That's all I write. And then my test work. Point2d01 is less than point2d10. Lexicographic ordering, yeah. Works too for binary trees. Binary tree of 3 is equivalent to binary tree of 3. Should be true, right? I lied, sorry, it doesn't work at all. So this is, I'd like to get through this in the last couple minutes and then try and get through the exercise a little bit, but like recursive types are always worth testing when you do derivations. They can be really hairy, and they're hairy in a variety of ways. It all boils down to you're going to make a self loop of somehow or another. Like I'm looking for the ordering of a binary tree of integers. Well, to find the binary tree, ordering of a binary tree of integers, I just need to have the ordering of all the elements of a binary tree, which includes a binary tree of integers. So let's find an ordering of binary, and then you're done. And it will either blow up at compile time or at runtime. I'm being very hand-wavy about this because it's very sensitive to things I don't even understand fully, like the actual structure of your derivation, your traits, and all those things can cause it to be a compile time blow up or a runtime blow up or whatever. Like you just need to test recursive types or tell people that they don't work. Otherwise, you'll be super emoji face. Fortunately, everyone knows this is a problem and there's a way to fix it, and it's built into Shapeless. This is a thing called lazy. And you just need to use it if you ever are working with recursive derivations like this. So how do you break recursive loops with lazy? Lazy is sort of defined like this. It's not because this is not valid Scala code, but it's the way to think about it. It's like a little box that is going to lazily have a value in it someday, right? If you define a new lazy, it does no work at all. It will just later promise that it will actually give you the value if it wants. It's the same as lazy val, just wrapped up into like a little container that you can pass around. The trick of that is that if I ask for a lazy ordering, then Scala has the opportunity to tie that recursive knot and just produce the one value. So, and I apologize for this, but I literally have not found any better system than this, and I've talked to people and no one's told me a better system than this. The way that I do it, because it's relatively fast, is you just slap things with lazy and guess and check until the recursive types work. There's some general heuristics to that, but it's actually really fragile. It's hard to guess when it's going to work. In this case, we need to apply it to 2 of them. We need to put it on the generic ordering of case class, that implicit def for generic ordering. I need to put the lazy around the ordering, that compare h lists, line 4 there. And then I also need to put it around the derive method. Fortunately, those are my 2 heuristics. Those derive methods, if you use them, it's pretty often the right idea to make the implicit there lazy. And the other one is, if you get a loop, just write out what the loop is, ordering, generic ordering, compare h list, ordering, forever, and slap a lazy in it. I tried it first with generic ordering, it didn't work. I tried it again with compare h list, it did work. Now, I then spent 10 minutes trying to think about a reason to explain to all of you about why it works, and I got some theories, and it took a while and it was really hard, and that's why I'm saying that you can get some general heuristics for it, but it's a lot of just try out different places of using lazy, do some debugging, try to figure out where your loops are occurring, and try to break them with lazy. And it's unfortunate that I can't today offer better. Try it. I don't think it'll break anything. Yeah, I don't think it'll break anything. That's true, yeah. Yeah, I've not ever seen anyone do that, but I think it probably isn't the worst idea. Yes?
Sorry, so the loop here is an implicit resolution, right?
Yes.
So Scala just goes bonkers?
So that's a great question. There's 2 ways that Scala will go bonkers. One, it will say, your implicit resolution is diverging. And it will fail at compile time, because it's looking for implicits, and in order to find the implicit, it needs to use the same rule that it just used, and it says, this is never going to work. It actually might work, it's just Scala is very conservative when it does that, and so lazy will essentially there's some macros in there that makes lazy implicit instances always exist as far as the Scala compiler is concerned, and then it looks up at a later stage in the type checking algorithm, so it causes it to stage that thing a little bit and break the loop. And the other one, the one that actually happens in this case if you go and do it, is the resolution is fine. It's just that it involves a def, and so when it actually defines the thing, it doesn't get a fixed point on that recursion. It just keeps calling the def over and over and over again as it tries to create one value. So you know you don't need to because all of your binary trees are actually finite, so you only need to call def so many times, but it doesn't know to do that, and it tries to just exercise the whole thing. So you hit it with a lazy, or in this case 2 lazies, and then it will tie that knot for you properly. So in this case, to make the recursive types work, almost always to make recursive types work, I would be willing to say always to make recursive types work pretty much, you have to use lazy somewhere, and my 2 heuristics are make the derivation methods lazy and then find the loop and stick lazies in it until it fixes itself, or do as this guy suggested, just put them everywhere. They're going to make it probably a little slower, but I don't think it shouldn't change the semantics at all. Cross my fingers. All right, so to define generic functionality over all case classes. Write a type level program that works over H-lists, transfer that functionality using generic, and then the last new trick, check recursive cases and use lazy to make sure that they actually work. Those are the basic tricks. So I'm going to talk about some too. We have about 10 minutes left. I could talk generically about Shapeless and like when it's useful, but people already asked some really great questions about the value of Shapeless. The only thing I'd really say is you've also got runtime reflection, you've also got macros. If you're really investigating a project about generic programming, you should consider probably all 3 of those. Shapeless is beneficial because it's simpler than macros and it's typed unlike reflection, which both will help your users because it will have these output types that they can then push their constraints off of. And it will help you because generic programming can be really complicated and having a little bit of type guidelines can help.
You said it used to be a Haskell programmer.
Yeah.
Did this come for free with Haskell?
It doesn't come for free, but you do it almost the same way. You used to do it almost the same way until about 7 years ago, and then they implemented another level of functionality, which you can also kind of do in Scala, but it works better in Haskell, and a lot of people are moving to that one. But you do this kind of type class prologue is a Haskell concept too. But yeah, try reflection, or think about reflection, think about macros, think about Shapeless. I can't offer much more broad sweeping things than Shapeless kind of gives you types, and it's a little bit simpler than macros. But think a whole lot about your users. If they start bumping into H-list types, they might be really scared and unhappy with you. If they start bumping into type class resolution issues, those are really tough areas to figure out. Have good documentation, support people, pair program, whatever it is. But if you can avoid all those things, then Shapeless is actually a really wonderful way to reduce a lot of boilerplate and define these very generic functionalities using just the structure of your types. So with that, I think I'm done talking. I'm so sorry for talking so much. I really want to get into practicing a little bit. We've got 10 minutes left in here, so I think I've got 2 more exercises I'll talk through. These are generic definitions of the size of any case class, like how many components does it have, or defining equality for any case class. It's just like order. You just search and replace ord for eq and it works, but don't do that. Or the hardest one, and this is one for people that really feel like they've got it now, interchange. If 2 types have the same structural representation, you should be able to coerce one into the other and back. So then you have to ask for 2 generic instances and pipeline all that stuff. So those are all the exercises that I prepared. I think this is a worthwhile slide. I hope everyone feels like they learned a lot about this, and I hope that by going through type level programming and talking about how it applies to generic programming gives you this compile time ability to manipulate types and coerce and have it write programs for you. Like that's what Shapeless is there for. That's why people like we could just have fun doing type level programming, but there are things that actually create a lot of lift for you, and that's kind of the shape of Shapeless, using these techniques together to get that boilerplate lift and to work at this higher level where types have both their nominal representation and their structural representation. So with that, thank you.